Hi everyone, my name's John, I'm from Lumin's workshop, and today we're going to talk about installing and designing circuits to put LED lights into your costumes. I've been doing this for quite a few years now, so I hope I can share with you some good tips and tricks and get you started into the wonderful world that is LED lighting. So yeah, I guess we'll have a bit of a rundown today of the main components of the system. We're going to learn how to design circuits, choose how you're going to power your item, and then I'll cover a bit of the actual installation. However, I don't have a piece of armor or a prop to install lights into today, but I'll hopefully at the end I'll just go over a few things to look out for, a few different techniques you can use to make the most out of what light you have as well, because that's quite a big thing. And then maybe at the very end, we might touch a little bit on Arduino, but given that sort of Arduino is a whole different kind of setup, you've got lots of different modules you can choose from, it needs to be programmed, all that sort of stuff. So it's really like a more advanced kind of tutorial. But with what I'll be showing you today, it'll be enough that you'll be able to make your own circuits from scratch. You'll be able to, should be pretty comfortable with using things like LED strip, and you'll know how to do some basic calculations to figure out how long your batteries are going to last. Have you got enough light for the whole day? As well as how to install your lights into your costumes to keep them safe and nice and protected and that sort of thing. So first of all, why do we choose LED lighting? Why is everything using LEDs these days? Well, why don't we use other bulbs, other forms of light, And the main reason is power efficiency. LEDs don't use much power and they don't put out much heat, but they put out a lot of light. So that's obviously really beneficial to us because we don't have to, carry around entire car batteries or generators to, have nice bright lights in our costumes. And the other reason they're really good for costumes is they're quite cheap. They come in thousands of different formats, from little tiny bulbs to, lots of chips on a strip to, really big flat plates of LEDs that are good for lighting like sort of large flat areas, sorry. So starting off, we've got a few major components in any sort of LED light system, regardless of whether it's Arduino based or whether it's just a straight hardware, plain LED light approach. Whether it's LED strip, whether it's individual bulbs, everything. You've got your power supply. It's going to supply power to your system. Now, arguably, this is probably, especially once you start getting into like larger projects with, either like large bright lights or very large lit sections, your power supply is going to become very important because you want to know that it's going to supply enough power to even light your project, as well as that it's going to supply power for long enough. And of course, this is going to come with a lot of trade-off because in a lot of costumes, you're not going to have a lot of room. So it's important to kind of choose the power supply that's right for you. So before we get into the technicals, we've got a few different types of power supplies. I'm sure everyone before has seen little batteries, whether they're 9-volt batteries like this big square one here, or these old coin cell batteries that I think we got from IKEA. You've got things like battery packs that have a lot of batteries in them. And then you've got things like USB power banks, which are becoming increasingly popular for Arduino projects. I don't have one to show you because it's currently powering some of my equipment over here. But yeah, so a power supply does two main things. So the first one is that, barring some very expensive, or generally more expensive specialty kind of laboratory supplies, a power supply, whether it's a battery or a power bank, is going to supply a fixed voltage. And you can think of voltage, which is one of our core sort of electrical units, the amount of energy that's available. It's kind of like if you think about a tap, when you turn on a single tap in your house, you get quite a lot of pressure. But you might turn on a second tap and you get less pressure. That's because you've got kind of a fixed water pressure coming into your house. So yeah, power supply supplies a fixed voltage, and then it will also supply an electrical current, which is just the energy that flows around the circuit. Now, the speed that the current flows around the circuit determines what the value or the strength of the current is. And something that's really important as we move through this is that a power supply can be rated for a certain amount of current. You might have seen a lot of USB power banks, like your really cheap basic ones will give you, so if it's a USB power, a standard is generally 5 volts, barring some of the newer like quick charge systems, which you don't have to worry about at the moment. And the standard I think used to be 1 amp. 1 amp of current, or we're going to use engineering notation today, so you just need to know that 1 amp is also 1,000 milliamps. Similar sort of situation to like grams to kilos. But because LEDs are so efficient, we're going to be working mainly in milliamps. Yeah, so if you've got a USB power bank and like an older or a cheaper or a smaller one, it might only do 5 volts and 1 amp of current, which is like a standard slow charge for a phone these days. And then when you move up to say a faster charge, like it's going to put more power into the phone, it might be 5 volts at 3 amps, that sort of thing, or 3,000 milliamps. So every power supply is going to have that fixed voltage. Now, a lot of things like these 9-volt batteries, I call them a 9-volt battery because they supply 9 volts, and it's generally what they're commonly referred to as. So usually with these type of batteries, your disposables, they'll just have a voltage listed on them. And you can use that as we go forward and do our calculations. Now, what's really important with power supplies is getting enough voltage. With the voltage, you just need to make sure that the voltage of your power supply is going to be bigger than what you're powering, at least equal to or larger. Now, you'll see here, we've got, I think, 8 AA batteries in this battery pack. This is one of our 12-volt power supplies for LED strip. But what you'll notice about the batteries in here, I'm not sure if you'll be able to read that, but not because of the lights. So each one of these batteries has written on it that it supplies 1.5 volts. So these are AA batteries. They're 1.5 volts. So we know that when they're new, they're going to give us about 1.5 volts. Now the thing with alkaline batteries when they're new is they're a bit higher voltage, but as they kind of start getting used, they drop down a little bit. So this is the first thing, the first little bit of theory here, is when you've got power supplies, especially if you're using a USB power bank, you probably won't need to worry about this because you're not going to be stacking them. But with like these type of batteries, generally 1.5 volts is not going to be enough to do much with. So you'll want to put them into a battery pack like that. So I'm just going to quickly draw the symbol for a battery here. So the positive side is the big side, negative side is the little side. So I said this was a 12-volt battery bank, but it's full of 1.5 volt batteries. So how is it 12 volt? So the thing we've got to understand about batteries is that you can connect them in line with each other, like I'm drawing now. And every time we stack a battery, so if they're all 1.5 volts, if you stack them in line like that, all the voltages add together, okay? And with this pack, there's 8 of them. I'm not going to bother drawing that. But if you go, so if we add 8 1.5s together, so 8 times 1.5 volts, we're going to get 12 volts. So pretty simple, right? Now you might ask, if you've seen this, this is actually what's called series connection, by the way. So when you're connecting things in line in electronics, that's series connection. Now with batteries, we can do another thing as well. But there is another way we could connect them. We could have one battery like this, and then another one connected like that, and so on and so forth. continuing on down and down and down. Now each one of these batteries still supplies 1.5 volts, but you'll notice that all the positive ends of the battery, so the plus side, on these boys, that's the little thing that pokes out. The flat side, the fully flat side, is generally the negative. But yeah, if we connect them positive to positive, negative to negative, so just in like a bank, this doesn't increase the voltage. What this does is it effectively enhances the capacity of the battery pack. So we've got 3 batteries there. We don't know what their capacity is because alkaline batteries don't list their capacity, or the disposable batteries don't list their capacity. Let's just say this is, if we delete those 2 branches there and it's just the 3 batteries like that, we've got 3 times the capacity, and every battery we add is just going to keep adding to that capacity. So this is called parallel connection. And this just, yeah, as I said, just increases capacity. There's a few laws, I say laws, but they're really just like electrical, things in electronics, like, how there's the law of physics, like the F equals ma, Newton's third law, that sort of thing. We have a few of those for electronics. So the first is called, I always say his name wrong, but it's like Kirchhoff's voltage law, or more commonly referred to as KVL. But that states that in any closed loop in an electrical system, the voltage by the time the loop is completed will be 0. And practically that means that when you have a battery, like so, you have your voltage coming out, so whatever it is. Then you go around here, you go through some parts, and you end up back at the negative side of the battery. So let's say you have 12 volts coming out of this battery pack. By the time you go around here, the voltage is going to go through this component here, and by the time it reaches back around there, there has to be 0 volts remaining. All of the energy in that loop has to be used up by the things in that loop by the time it returns around back to the start. So that means no matter how many parts we have in there, no matter how many components, it's going to be gone, right? We can have no components there, but it'll have to be gone even if it's just a wire connecting the 2 ends. The second one is Kirchhoff's current law, or KCL. The current in any loop of an electrical system will be consistent the whole way around. And you can think of this like if you have a pipe or a loop full of water. If there's nowhere for the water to go and there's something pushing the water, it's going to push the rest of it and it's all going to move because it just can't flow anywhere else. And this becomes really important because it means that we know that we know the current for things that are in series with each other or in line with each other, and that really helps. So just to illustrate that again, so we've got here, we've got some sort of component there. So our current's going to flow out of here. Now I said before that the amount of current that we have is going to be determined by the components we have in the system. Like even if a power supply is rated for a certain current, you're not going to see, it's not going to necessarily put out that current. It will only take what the circuit wants. And yeah, so we're going to come back and we're going to do this loop. So if the current is 1 here, it's going to be 1 here, and it's going to be 1 here, and it's going to be 1 here. So those 2 on their own are pretty simple. We've just got one that says all the power has to be used up by the time it returns to or finishes the loop, and we've got one that says that any loop, the current is going to be consistent all the way around. And that's kind of where these sort of parallel and series battery configurations come in. So we've got in the series one up the top here, every time it goes through a battery, it's adding 1.5 volts, but by the time it gets back around, it has to be 0. And the batteries themselves are supplying power, not taking it, so they're just going to add together and have however much voltage available for the rest of the circuit. And the parallel increasing the capacity, we've got 3 entry points into the batteries, or into the negative side of the batteries, or 3 entry points. But we've also got 3 points that the current's coming out. So if we have something, so if we have a loop here with something here, we've got, one current there, one current there, one current there, but they've only got one way they can go and complete a loop. So we've got 3 currents there in a general form, just using generic units. So remember this as we go through, because this is quite important for connecting multiple LEDs and making sure that we have enough power. What you might have also seen, especially on USB power banks, is a capacity rating. So, it might be a 20,000 milliamp hour battery pack, 20,000. And that equals 20 amp hours. Just to convert that yet again. And what that means is that battery pack is rated to supply 20 amps worth of current for 1 hour. And then you can use that ratio to kind of figure out how long something's going to last. So if you needed something that was drawing, or if you had a circuit that only needed 1 amp, then you could power that for 20 hours. If you had something that draws 5 amps, you could do, that's 4 hours. So you can use that as kind of the capacity rating as kind of a rule of thumb to just figure out how long your batteries are going to last. So there are a few different disadvantages and advantages of different battery types. Obviously, having a battery pack like this 12 volt thing, is really nice and easy. You just slap some batteries in it, it puts out 12 volts, the batteries run out, you replace them. Simultaneously, a USB power bank is very convenient because it's got the charging built in, and being usually being made with a different type of battery called lithium ion, which is very power dense, very powerful. It has all the protections and stuff built in usually that will stop any sort of danger from those batteries being short-circuited. And when I say short-circuited, that just means that if something were to go wrong in your cable, or you're doing your project and you accidentally join the 2 ends of the battery together, just with a piece of wire or something, rather than having something in between, what can happen is that it just puts way too much. It'll just, basically there's nothing stopping the power from flowing. So it will supply as much power as it possibly can, which with a very power dense battery and no protection can be quite dangerous. But these days, those type of things are built in and are just present as part of the battery to make them nice and safe to carry around in your backpack and that sort of thing. Now you can buy just lithium ion batteries together on their own to put in your project. I actually don't have any here because I usually use power banks these days just because they're convenient. But yeah, there's a whole sort of setup that you can buy from companies like Adafruit where you can buy just the little raw cell and then a little charging board. I should also mention that all the power supplies we use for LEDs are generally what's called DC, or direct current. And basically what that means is the current only flows in one direction. So it'll go from the positive side of the battery to the negative side of the battery. Now in stuff like your wall sockets, your power lines outside, that sort of thing, that's called AC power, and that's a very different beast entirely. But you just want to check, and it will usually be written on it. It'll say, input 240 volt AC, output whatever volt DC, and then some sort of power rating for it, some sort of current ratings. Don't plug anything directly into a wall, even if you've designed the circuit to take 240 volts. It's not a good idea and it won't work. You're generally a lot safer to test on batteries or to use something like a USB power bank or a dedicated DC power supply as well, which is you can buy those online as well. But they are a bit of an expensive bit of kit, so I'd generally use batteries when you're starting out. It's just a lot easier, a lot simpler, you can move it around. So now it's time to talk about LEDs, and we want to know, how do we pick LEDs? What type of LEDs are available? Okay, so I've just got a little box of LEDs here. These are your like traditional, like very kind of basic style of LED. You can see there, it's just a small clear bulb. It has, has two legs coming out of it. If you can, if you can see that. And yeah, so that's your basic style of LED. Now they come, so you can get them in smaller types like that. But there's also a few new styles. Luckily, they all work pretty much the same. So I don't know if you can see, this is just a quick demo I will show you in a minute, but this is just a little pre-bought light switch. And you can see there's a whole sort of flat plate of LED. So that's quite cool. So I'll start with our most basic type. So this one's a pink LED, but so yeah, on this strip, you've got, see those little square chips there? So each one of those is an LED. It's actually 3 LEDs in each one. There's 3 little spots on each LED. And the good thing about LED strip like this is just a 12 volt LED strip. So what I can do, it's really simple. No need to make a circuit. Usually I have a little plug for this, but I'll just, for the sake of demonstration, plug that in. And then, you know, we get a nice strip of LED light, which doesn't look very bright because I'm under very bright studio lights, but trust me, it's really strong. So yeah, this is your basic 12 volt LED strip, nice and easy to use. Obviously you've got connection points you've got connection points every 3 LEDs. You can trim those and then just take the silicon off using a knife, which if we've got time later, I'll actually demonstrate. And yeah, so cut it into whatever length you need, as long as it's on one of these sections, and then you can just solder to the little copper tabs there. Second type of LED strip. Now this is the same, you won't be able to see that because it's quite a short roll. So this is the same type of LED strip, same type of LED, except instead of 3 of one color, it's got 1 red, 1 green, and 1 blue, commonly referred to as RGB. So with this one, you've got 4 connection points on each strip, on each section. So you've got 1 for your red, 1 for your green, 1 for your blue, and then the negative that finishes the loop. Back to your battery, or the ground as it's commonly referred to. And this type of strip's good because you can choose whatever color you want. On our store as well, and other places, you can get remote kits that you can just plug in. So you can just connect a 12 volt power supply, like this one, into the remote kit, which I unfortunately don't have with me today, and then into the LED strip from there. And you can choose the color of light you want. Sometimes they have patterns available, sometimes not. It depends on the controller. So the final 2 types are here. So this is their last 12 volt LED strip that we've got. And this stuff's quite new. As you can see, there we go, if it focuses. So it's 1 solid bead down the middle, like I showed with the little light switch before. So this is like a lot less dotty. Unfortunately, we do have wires. I should be able to show that. I try and keep as much stuff kind of put away as possible because it can get very messy very quickly. So yeah, you can see there, compared to the other one, it's a lot more of a solid sort of strip of light. So this is good for places that are a bit tighter because it's a thinner strip, as well as if you need lights really close to the surface or you need like a very solid, line of light. And the final type of LED is another one of the chip LEDs, like the first 2 that I showed. But this one's a little different. You can cut it at each LED, and this is a 5 volt LED strip. Now we don't have this in our store, but this is the stuff that you commonly use with Arduino. So you can use your Arduino and you can actually control, like you could with the other RGB strip I showed, you can actually control each individual LED light, which comes in really handy when you need different colors along a length, or whether you need to have a pattern, you want it to go from one end to the other or move around and stuff like that. So that's one advantage of going with like an Arduino system. So first of all, I'll just draw the circuit symbol quickly. So it looks like a triangle with a stopper, usually has a circle around it. And yes, it does actually have 2 lightning bolts, because without those, it means something completely different. So yeah, now some of you might have guessed, but LEDs do have a direction. You can't just plop them in the circuit whichever way you want. So you need to put them positive side, negative side. You'll see that there's actually, coming out of the bottom of these normal LEDs, there's 2 legs. One's longer than the other. Then you have the bulb. And if you look very carefully from the top, you'll see that it kind of goes like that. So if there's the 2 legs there, that's the positive side, that's the negative side, that's the positive side, that's the negative side. Other LEDs, like the chip LEDs, are a bit different, and the data sheets for those are usually online, but if you're using it in an LED strip, it's generally just labeled on the strip itself. So LEDs need 2 things to function. First thing we need is a voltage, and this is generally referred to as an operating voltage or a forward voltage. Some LEDs will have a range, and I would generally either go the middle or at the top of that range, or whatever works easily with your battery. But they also need a current flowing in the circuit to go. And that will be called the forward current, the operating current, sometimes called the max current. And this, if you're looking at a data sheet or asking someone you're buying LEDs from what it is, they'll just be listing generally the highest current that that particular LED can take, and still run continuously and not burn out. And to do that, we'll need another component, which I'll talk about in a moment. But for now, we just need to know that we need an operating voltage, also called a forward voltage, and a max current, or a forward current, depending on who's written the data sheet. So we have just our normal LED here, and this is just a little LED tester. It supplies different currents to the LED, and just a fixed voltage that does pretty much every LED. So I grabbed a blue one, I think. So if we start at the low end, so yeah, you can see it's quite dull on the 0.5 milliamps setting, but if we move up to 10 milliamps, you can see it gets, I don't know how bright that is on screen, you can see it gets quite a bit brighter. And then this LED is rated for 20 milliamps there. LEDs have a maximum current, and that the power supply or your battery will supply will only supply what the circuit wants. So the next logical step is to tell the circuit how much we want. Now the problem with LEDs, because they're so small, if they do heat up, they heat up very quickly, and by very quickly it'll heat up and blow, typically before you can react. So I don't know if I'm going to catch this on camera because it does happen very quickly, but this is going to be putting an LED with a power supply that's A, much too high voltage, and B, it doesn't have anything to control how much current it's got. The LED is just going to take whatever it wants. And a thing to note is that as it gets warmer, the kind of resistance to taking current drops. So it's going to want, it's like the hotter it gets, the more it wants. And it continually just gets hotter, takes more, gets hotter, takes more. Yeah, see, it's done. That took all of about 1/4 of a second, and that's gone. That's never going to work again. control that the LED is getting the correct voltage, its operating voltage. And we also need to ensure that we have something in there that's going to bottleneck our circuit and stop it from supplying too much power. And thankfully, this is really simple to do with our final component, and that's called a resistor. So resistors, they're just each one of those little blue beads in there. Now these are quite low power, which is why they're quite small. So they're suitable for what we're doing today. But yeah, these are just basically little bottlenecks in the circuit. So as if you put a tap on the pipe and you're only, screwing it open a little bit just to let a little bit of water through, or a little bit of power through in this case. This is our final kind of electrical rule, electrical law that we need today, and then that's literally all you need for maybe 99% of the stuff that you're going to do on this sort of level. And this is called Ohm's Law. And that is V equals I times R. Now, just to reiterate, I did mention it before, but I didn't sort of specifically mention it. So when we're doing our units, our V is volts, just volts on its own. Our A is amps. And our R is resistance. However, you'll also probably see it written as a little omega symbol like that. So yeah, every resistor has a certain number of resistance, and that just says how much it bottlenecks the circuit. The higher the resistance, the more it's going to bottleneck the current in the circuit. So for those people who maybe struggle with algebra, you can also rearrange this into two other forms. I equals V divided by R and R equals V divided by I. And you just need to make sure when you're doing this calculation that everything's in a standard unit. But as I mentioned before, with our current, we're mostly going to be working in milliamps. So if you need to convert a milliamp, which is what you'll see on like an LED data sheet, or when you buy an LED, it will have a milliamp value that you need to use for your current. All you need to do to convert that is to divide it by 1000, and then you can use it in this equation. So we've got this law, that's all well and good. How do we use it? So first of all, I'm going to draw the typical, just a standard single LED circuit. It's the most simple LED circuit you can make. Yes, if you're doing one LED, it's very simple. It can get more complicated with multiple LEDs, but generally it stays pretty simple. So we've got a battery here. So minus, plus. Now I'll just put a new symbol in because generally we're going to put some sort of switch, some sort of mechanism to shut off the power. So a switch will generally look like that on a diagram. Now there are other types of switches with multiple entrances, multiple exits. I'll just stick with the single switches today, but just know that there are options where you could have something like this, where there's 3 possible ways it could go. So you could run it to 3 different loops. And choose between 3 different things. Just be aware that that's an option. If you maybe need to switch between 2 colors or something, you could put 2 different colors of strip in there, or use an RGB or something like that, and just connect different parts of it. But yeah, so we have our battery, we're followed by a switch. Now, so we come around. I'm going to draw in our resistor, which is just a rectangular box. Sometimes a resistor will be drawn as a box. Just a little squiggly line like that. Sorry, that was very poorly drawn. But yeah, so we come through from the battery, we go through our switch, we come to our resistor. I'm just going to call it R1. We get to our LED. And then we come back around to the end. So LED 1. So you're probably wondering, how do we how do we make this circuit now? How do we calculate what we need for the circuit? So the first thing we need is information about our power supply, and we want information about the LED. At this point, we know the resistor is going to be a bottleneck, but we don't know how much of a bottleneck it needs to be, so we can't pick it out yet. So I'll just call this the voltage of the battery VB. For simplicity's sake, we're just going to use the 9-volt battery for our demo later. So we'll go voltage battery equals 9 volts. What other voltages are we going to have? We're going to have the V of the LED, so VL1. Just when I write the little figure like diagonally right of the voltage, I'm just saying it's for that component. So voltage of our LED. Now, what color do we want to use today? I'm going to choose a green one so it's nice and visible. So for my green LED, my data sheet says, and when I say data sheet, it doesn't have to be like a huge technical document all the time. Most LED sellers will list the correct voltage for the LED and the correct current for the LED, just in the listing if you're buying off eBay or from Lumins or wherever. So this one just happens to be written on the box. So it says 2.8 to 3 volts. To make calculations simple, I'm just going to say 3 volts. And then, so the only other component we have here is the resistor, so VR1. And we don't know what that is yet. But thankfully, we've got this little law from before, the Kirchhoff's voltage law, KVL, that says that any voltage coming into the circuit, by the time it finishes the loop, it has to all be spent. So we know that we're going to have 9 volts coming in, and we're going to have 3 volts eaten up by the LED. And there's no other components, so that's all we have to consider. So it's just 9 volts, 3 volts is going to be eaten by the LED. So we're going to have 6 volts remaining. So we now know how much voltage is going to be in our resistor, or going over our resistor, or how much, you can think of it as how much voltage it needs to soak up in the circuit. Now we also have that other law, so we need to figure out how much current, or we want to restrict the current in our LED so that it stays at whatever it says on the data sheet, which is 20 milliamps in this case. Oh, I should also mention, because of the current law, wherever we measured current in this circuit, I'm just drawing in arrows to indicate measurement points. We know that because this is just one single loop, we know that the current is going to be consistent the entire way around. So we can just say the current in this case, and we want it to equal 20 milliamps, because that's what's listed on my data sheet. So that's going to be the current through the LED, it's going to equal the current through the resistor, and it's going to equal the current from the battery. All those things are going to be the same. So if we take 20 milliamps, we know that the I in the resistor will be 20 milliamps, and we already have calculated that the voltage in the resistor is going to be 20 milliamps, is going to be 6 volts. So now we just need to calculate the resistance, and then we have our value. So from before, this one here, R equals the voltage divided by the current. So R equals 6 volts divided by 20 milliamps. Now we need to convert that milliamps into amps. So if we divide that by 1,000, it's 0.02 amps. And I'll just get my calculator out here. So 6 volts divided by 0.02 amps. So we get R equals 300 ohms. Or 300 R. It doesn't, unless you're doing like formal electronics, the correct units really don't matter if you find it less confusing to just use R. Okay, so that's it. That is just a basic, the most basic LED circuit design. And you can see it really takes all of about 5 minutes to calculate once you know how the voltage is interacting and how the current's interacting. Something important to note here is that especially if you're using a USB power bank to light some LEDs, and you're going to be drawing more than, say, the 1 amp of current or something, if you've got a lot of LEDs, is the power bank will generally just shut down if you do that. So it's always worth just testing little bits if you think something, you know, if that could have potentially been the issue. You know, if you might not necessarily have something else wrong, it might just be that the battery's been overloaded. Multiple LEDs is very simple as well, using these same laws. So we've already got this circuit calculated up here. So if we want to expand this circuit and add more LEDs without having to calculate again, we can do our parallel connections. So that would be, so we're not going to change the battery or the switch, and we're going to put that first LED in here. So we finish that loop. So now we just add a second LED. So there we have two branches. Now, using the voltage law again, we've got 9 volts in. Now I said we didn't need to do any more calculations here, and that is correct. So we've got 9 volts coming around here, but it's got 2 places to go. There's 2 loops in this circuit, or 2 ways that the voltage can get eaten up and go to ground, or go to the negative side of the battery. So we've got our first branch here, and our first branch here. But because they're both connected to the positive side of the battery, you're going to get 9 volts through that branch and 9 volts through that branch. So then it just becomes 2 instances of the same circuit but connected to the same battery, which is really handy. It's a little bit more work because you've got to connect more things, but this means that you can just keep connecting, you know, repeating the same thing, the same little circuit over and over again that you've already calculated, and you can just keep adding LEDs that way. But yeah, so this is a good method. It's a little bit more work because you've got a resistor for each LED. So there's a few more things to solder, but it's good because you don't have to constantly recalculate. Now you don't have to do multiple of the same, because each branch that you add on, each next loop that you add in is going to get 9 volts. So you can just, if you need a different color, you can recalculate for that color based off the 9 volts and how much current they need, and just do it in the exact same way as the single LED circuit. The only difference is going to be is that obviously each LED still needs to get its, in my case, 20 milliamps. In your case, it might be different. So each branch still wants its 20 milliamps. So our voltages are still the same, but our current leaving the battery and going through the circuit and returning to the battery has to be the same the whole time. But there's now 3 loops. So effectively what's going to happen is each loop, each branch requires that 20 milliamps. So we're going to have 20 milliamps here, 20 milliamps here, and 20 milliamps in the third one. So in total, there's going to be 60 milliamps, which needs to come out of the battery. It's going to flow through. It's going to split 1, 2, 3 times as I've drawn it here. And then those 3 ones are going to come back out, join back together, and there'll be 60 milliamps completing the loop. So the main thing with adding batteries in parallel like this is that every LED you add draws more power from the battery. Now there is a way you can add a different way you can add multiple LEDs, and I'm sure how things have been going, some people have probably guessed, and it's going to be series. So with the main thing with adding things in series, especially with LEDs, because the current is going to be the same as you go through each LED that's in series, you need LEDs that are compatible with each other. So you can't, put 50 milliamps through an LED that takes 50 milliamps and then put an LED in there that only takes 5, because you're going to blow up the 5 milliamp LED. But the one advantage of series is that current is already flowing and that voltage coming out of the battery is fixed. So what it actually means is you're not taking any additional power out of the battery to add that second LED on, or maybe that third LED on, as long as it's all in the same series branch. And you might think that doesn't make sense because you're getting more light, you're getting more power, getting more light from the battery, it has to take more power. But what's actually happening is you're just going to be bottlenecking less power from using that resistor. The resistor is going to be chewing up less power. So if we do our 9-volt battery again, like I think this is super nifty, but like bigger, higher voltage batteries are not necessarily the most practical things. Usually, because a lot of the time when we're doing circuits, really simple circuits like this, we're really pushing to get the smallest possible circuit. And a big, like higher voltage battery like a 9-volt can usually be a bit too much to hide unless you hide it somewhere else on your costume. So I haven't really done too much series work. I usually work in parallel so that we can use smaller batteries, especially in things like crowns and things you don't want cables coming out of, unless you get creative and run it down the back under your hair or something like that. But yeah, so continuing on just quickly. So we come in here. Now, our LEDs before took, I think it was 3 volts. So I don't want to use all the voltage because then I have no way of bottlenecking the current. So for this example, I can only put 2 LEDs in. So we want our resistor, our little bottleneck, VR. And then we want 1 LED, 2 LED, and we'll come back around the loop. So yeah, this is kind of cool, but yeah, as I said, I don't really use it that much. So VL1, L1, L2. So once again, we do this example in the same way as we did the first one, we've just got that additional component. So I'll move through quite quickly, and I'm sure you should be able to watch through this again later if you want to follow through step by step. So our voltage from the battery minus voltage from LED 1 minus voltage from LED 2 minus voltage from the resistor equals 0. So 9 volts minus 3 volts, because VL1 and VL equals VL2, because I'm going to use 2 of the same LEDs, is 3 volts. So minus 3 minus VR equals 0. So VR is going to be 3 volts. So it's going to take the remaining 3 volts. So that's the first half of what we need. Now we already know the current because we know that that LED takes 20 milliamps and everything in that loop is fixed at 20 milliamps. So fantastic. So 20 milliamps. So the current through the resistor is going to be 20 milliamps, and that's going to be the same as the current through LED 1 and the current through LED 2. So easy. We just do the same calculation again. Resistance equals V divided by I. So 3 volts divided by 20 milliamps. And again, that's 3 volts. We've got to convert that to amps by dividing it by 1,000. And that should, just double check it, because old habits die hard. And now we can see we've got 150 ohms. So it kind of makes sense, right? We had 1 LED before and we had 300 ohms, or a 300 ohm bottleneck, 300 ohm resistance. But now we've got the second LED is taking another 3 volts, so now the voltage across the resistor is halved. So it kind of makes sense that it only needs half the bottleneck, if you can kind of see that. But yeah, so that's 2 ways of doing multiple LEDs, if you're wanting to do them from scratch. Now, obviously, using something like LED strip is super handy because you just connect as many sections as you want and they've figured all this out for you. But this is really good for like when you need custom lights in places, when you need to place them a certain way that you can't do with LED strip. And that's generally the only time I use them these days. But it's just a really good learning exercise doing it this way, because then you kind of get an understanding of how different components and how voltage works in a circuit. Like, it kind of demystifies it a little bit. So you can combine the parallel and series methods. So we could take the loop that we just made and repeat that down the same as we did above, because that calculation won't change yet again. So we've got a few tools that we're going to use in both our circuit design sort of phase and checking stuff, and we've got a few tools that we use to actually make the circuit. The first tool I've got to show you is a multimeter. Now, if you watch a lot of, this isn't an essential tool. If you're going super budget, you want to do things as cheaply as possible for your first time out, you don't have to buy one of these. You're completely fine to do stuff without them. And what this does is it just measures stuff in circuits. That measures AC voltage, so I'll swap it to that one. This measures DC voltage. So for example, if you don't know whether, you've got a 9-volt battery here and you've been using it for a bit, you don't know, how well charged it is. You just grab your 2 prongs, make sure they're plugged into the correct one, so the common port and the voltage port, and you just put it across. Now it's important that you put it across, and so in parallel with and not in line with whatever you want to measure. So put it across whatever you want to measure. This is a brand new battery, and you can see there I'm measuring nearly 9.6 volts. So I know that battery is brand new and it's hardly been used whatsoever. Similarly, I've got this whole 12-volt battery pack I was using before. So let's just have a look at that one as well. This is going to be a bit hard because it's a bit fiddly to do when you're trying to do it with one hand. But yeah, that's been used, this one's pretty new, but it's not fresh. So it's just above 12 volts. So yeah, super handy. You can also click it over to the omega setting and measure a resistor. So I kept these in their bags to make them nice and easy to distinguish, because otherwise you have to either measure them or learn the resistor color code, which I'll leave you to Google that yourself, because it's a little bit complicated, and you're better off just to measure it or keep the stuff in their packets, because they're tiny little components. So you can see there I've got my resistor, this tiny little grain. It's got all these little color bands on it. So yeah, if you Google resistor color codes, it'll tell you what they mean for either 4-band or 5-band resistors, because there's different ones. But yeah, so I've switched it to the omega symbol, the resistance symbol. And we can see there, 99.7, so it's pretty good. This is let me just check. Yes, this is a resistor with a 1% tolerance. So it's within, if it's 100 ohms, it's guaranteed to be within 1 ohm unless it's faulty. Now this is probably, if there's one reason to buy one of these, it's for this setting. And you can see there's a little symbol there that's very similar to the LED symbol. Now I've got to put it on the correct thing. So I'd move it I'm just moving it to a different mode. And what this does now is it tells me whether something's connected by beeping. This is really handy once you've installed things and you're troubleshooting why something no longer works, especially after using a costume a couple of times. Because costumes, especially with movement, can become a little bit faulty, and then you'll need to remake the connections. And the last thing this does is, of course, measure current. Current's a little bit different to measuring everything else here. So current, you have to actually break a circuit, so separate it, and then measure in series with where you want to measure the current. It has to go into the loop. We've got a soldering iron here. This is connected off screen to, let me see if I can get it on screen for you, because it's quite big, this unit. So this is a big solder station. It also has a small heat gun. So this is just a very tiny hot air blower, and if you watch, there's a guy on TikTok who repairs a lot of circuit boards. They often use these just to precisely apply heat. I mainly use it for heat shrink and just bending small plastics, just because it's more convenient than a full-size heat gun. You can get very good, relatively inexpensive soldering irons on eBay, which is where I got mine actually. And they will generally come up, the ones that I've seen that seem to be a bit better are the ones that are designated as ESD safe. And what that means is that they've just got protections on the iron itself so that static doesn't go onto the tip. And that's important if you solder chips, but they also tend to have digital temperature controls that are pretty good. Now, the other thing you want for your iron, you don't have to have it, but I would highly recommend some sort of stand. Now mine comes with this thing because it's meant to be like, I think you can like bolt it down to stuff, but it's really convenient. You can put your iron in there so it's protected and you can't touch the hot tip. And it also has a spot for this sponge here. And you just lightly dampen that sponge. I'll just use a little bit of my water from the glass here. And we'll just let that moisten up. And the sponge is just for cleaning the iron once it gets too much solder on it. Always leave solder on your tip when you're turning it off because it helps protect it from corrosion. But yeah, you'll need, as you solder, you'll see the little balls of solder in there where I've just had to clean it off. So this is our core tool. This is basically just going to be, I never explain what a soldering iron does, but I'm sure you know it's used to melt a special metal called solder, which is just this stick here, which is just a low temperature alloy. And you use that to just effectively glue metal parts together or weld metals together. Now I should quickly talk about what solder we're using as well. So this is stock standard lead solder. So it's, I think it's, let me get it correct. So it's 40% lead. Now, and this is also what's called a flux core solder. So this is a really good solder to start out with. The main reason for that being that flux core solder has this, so it's a layer of metal. It's like a really thin metal tube with like a liquid resin inside. And what that does is when you solder, the liquid comes out and it goes around the joint and stops it from oxidizing, stops it from rusting and becoming dull. So you get a really nice joint. So this type of solder is good for beginners because you don't have to apply the liquid separately. But yeah, a temperature controlled soldering iron is key because the non-temperature controlled ones tend to get too hot and they, not all the time, but they can make the lead smoke, which is not great. Like it's just generally something, like it's a small amount of smoke, but you just generally want to be safe and avoid it. So the only other essential tool would be a pair of side cutters. And you use these for cutting wires. You can use them to strip the plastic off the outside of the wire, which I'll show you in a minute. So the first one, now this looks very intense, but I've got a less intense version as well. This is a wire stripper, so an automatic wire stripper. So you can see that there's a little jaw there and it just grabs a wire and then drags one half of it away. This is another really basic wire stripper. I generally don't use this because I've got the other one, but it's got the little teeth here. The final thing here, or two things I should say, are solder removal tools. So you use these when you mess up. Now, I haven't really used solder braid much before. That's what this is called, or solder wick. But basically, it's just a lot of very thin wire. So you put this over the messed up joint, you push down on it with the iron and you let it heat up, and then all the solder will get sucked up into this like a sponge. And the other one here is a solder sucker, or I think it's like a suction pump. I can't remember the actual name for it. But you click this down, you get your soldering iron in this hand, you heat up the solder so it liquefies, you put this right on top and do the little pop there. You're looking at something like this. It's not a very practical form factor. It's very large, it's fat, the LEDs are stuck in place. There's this huge switch in the middle on the front that needs clearance if you were to mount it in something. So it's not ideal. So we can just modify this. So I have the inside here. So it's really, really simple. It's just, as I said, this was $3, so we're not expecting anything earth-shattering here. But we've got the 2 battery packs that come out here. And then there was the switch connected onto this little metal plate here. And then we just had another piece with the 2 LEDs on it, or the 2 plates of LED. And then it just goes back through this big resistor here. So it's exactly what we had before with that, the 2 LED parallel circuit, but with 1 resistor at the very beginning. All I've done is I've taken the little short wire there and just put a little red one. So I've lengthened that so it can sit up higher. And then we'd just put another long wire in here. So, if you needed to, light some eye holes in a mask, or, 2 little strips on like that's what I was thinking of, like the Mass Effect pack I think has light strips down each side. So that's one way, is you can buy something pre-made like this and then just keep the battery component and extend the wires on the LEDs, and you can modify it a bit and all that, because you don't have to change anything about the circuit. You're just lengthening how far each thing is away. Using LED strip is pretty simple. As I said before, we're just going to join our 12 volts onto here. This is an RGB one because it just happened to be an offcut that I had, so I won't be connecting it up. Look, it's not a super complicated thing. All you have to do is come in here and remove that tiny bit of silicon, and the way that we do that is just by getting a Stanley knife, holding it down low and just gently sawing it backwards and forwards until it's far enough through. Then you're going to come in here with the blade and just get between, you can get underneath, like pick the corner of the silicon up because it's just stuck to the LED strip, and then you just rip it off, and it comes off fairly easily if you're cut in deep enough. With the LED strip as well, I should mention that if you want to protect, once you've exposed this end, if you want to protect it, you can use something like heat shrink. I wouldn't use electrical tape because it tends to degrade over time and start coming loose. But you can buy heat shrink, which is just this tube here. It goes over the joint. You can obviously cut it down. I just haven't cut this piece. And then you just cover it and heat it up with either a cigarette lighter, or if you have a heat gun, you can use that as well. But you just have to heat it across the thing and it shrinks down. So first of all, we need our LED. So again, I was going to go with the 3-volt green LED today. And we calculated a 300 ohm resistor, I believe. So there's a couple of things I can do here. I've got 100s, I've got 220s, and I've got 470s. So I could connect in series a 100 and a 220. And that will get me, when resistors are connected in series, their resistance adds up. So like you're adding an extra bottleneck. So that's a good option, but really it's probably not going to be that important if I go over. The 470 is 50% over. So if we raise the resistance, it's going to take more from the LED. It's going to reduce how much current's there because the voltage is fixed. The LED is always going to take that 3 volts. So we know that the resistor is going to have 6 volts remaining in the circuit that we're making here. And we know that the LED we want the LED to take 20 milliamps, but because if we choose the 470, we're going to be increasing our bottleneck. So we can just calculate, because we know what the resistance is going to be because we're picking the component, and we know how much voltage is going to go through it because that voltage that the LED is taking is fixed. So I equals V divided by R. So 6 volts divided by 470 ohms. So in that case, we're only going to have 12, nearly 13 milliamps coming through the LED. So what we were aiming for with our 300 ohm resistor is this. But what we're going to get if we use the higher value resistor, so the 470, is going to be more like that. So you can see there is a pretty big difference here. So just be aware if you're choosing a value higher, if it's a lot higher, it could affect how bright your lights are. So for the demo, I'm just going to use the 470, even though it's a little duller than intended. Now, let me just see. So the last thing we're going to need is some wire, which I've got there. And we just need a 9-volt battery clip, which should be hanging out around here somewhere. Here's one I prepared earlier. So this is just clips straight onto the 9-volt battery. And then This happens to just be pre-soldered with a little clip. This is, I think, just called a clip tether or something. But you can get a lot of clip connections like this, and I would encourage you to have batteries that can easily disconnect from your circuit. So, for example, here's just a set of what's called JST connectors that I got online. But yeah, so I've already soldered the wires here. So what I need to do is put 2 wires onto this bit. I need to run the resistor and LED side of the circuit effectively. Something really important as well, just when you're looking at circuits. Red is generally the positive, or goes to the positive side of the battery, and black is generally the negative, but not always. Some places use white or whatever other color they've chosen, but generally it will be black. If you see other colors in a DC circuit, like green or yellow, you might be looking at some sort of data line, but that can vary depending on manufacturers and what they actually decide to do. Now I like to color code my wire. If you want it to blend into your costume better, feel free to not color code it, but just be aware to keep a track of what's what, because sometimes you'll be installing stuff and then you'll just not be able to see your wires, and then you'll have a hard time connecting the correct side of the LED. So I'll grab one of these 470 ohm resistors. And so one last thing, sorry, before we begin, that the demo can be really helpful is this little thing here. It's basically just a weighted base with 2 claws. They come in a lot of different formats. This is a super basic one. But it's not essential, but it can be really helpful. I just call them helping hands. I don't know what they're actually called online, but these clips are just really handy to grab stuff with when you want to hold wires in place, anything. Anything that they fit around, it's just helpful for them to hold. So the first thing we want to do is prepare our wires. I'm going to make this about 30 centimeters long. Just guessing here, it's not super important. The only thing I do want to do is make sure they're both the same length, because that will make it a lot neater at the end. So this sort of technique is really good for putting a single light in stuff, or possibly multiple lights if you want to. For lighting large areas, I would generally just go for LED strip if you can fit a 12-volt battery in. That's the simplest way to do it, because it's just, you don't have to do all the soldering to put each LED in yourself. It's just a lot easier. All right, so first we have to prepare the wire. We can't just solder it as it is, because as you can see on the on the end there's nothing to solder to. It's just plastic, and if we heat that up with the soldering iron directly, it's going to gum up the end of the soldering iron, and that's just not very good. So I'm just going to use my fancy wire stripper to do this one, and I still have it set really large, but that's okay. I'll trim that up later. So it just goes in, gets pulled off there. Whoops. There we are. So I've got exposed ends of the wire. You can see already that the longer one there that just got stuck in the machine, got a bit longer, it's already starting to fray. So once you pull the wire off, you really want to go and just twist them. Make sure they're nice and twisted, so they're nice and neat. Okay? So that's just using the clip machine. As I said, very easy. If you want to go like back to basics, learn how to do it the super basic way. Flat side of the cutters outwards. You don't have to have the fancy polished ones. It works absolutely fine with a decent pair of just cheap side cutters like you might already have for like beading or stuff like that. The flat-sided ones just give a flush cut when you do wires, so it's like a bit neater on circuit boards and stuff. But to do that, all you're going to do is just grab the wire in there, squeeze gently. Now these are very sharp, so this actually makes it a little harder, but you kind of just hold it so it's pinching the plastic, and then you just pull it off. And the most common mistake I see people make when I run my LED classes in our workshop is they just clamp too hard and sometimes take a couple of filaments of the wire out. So yeah, again, you just enough to pinch it, you can kind of feel it, and then it just comes off like that. Okay, so I've twisted the ends of the red one as well. Now we want to strip, so we've stripped the wire, now we need to tin the wire. And by tin the wire, we're doing a couple of things. One, we're stopping little stray filaments from going everywhere. B, we're like pre-tinning, pre-soldering the wire so that when we go to actually solder it, it gets a really good connection and heats up very easily. And that's honestly the main thing, because then like your filaments don't go everywhere and you just get this nice like good flow of solder. Okay, so if you're a beginner and you're not too confident around a soldering iron, a helping hand is really helpful here, because you can clamp the wire while we're working on it so you don't have to touch it. That's really simple, like pretty self-explanatory. I have a bit of a weird way of doing it. So you notice here I'm holding the soldering iron down with the tip off the table, and I'm stopping it from rolling, and I'm holding the solder in the same hand, and you've got to kind of get the length so that I can get to the tip. Let me move that more central so you can see a bit better. So now, pretty simple. I'm just going to put a little bit of solder on. That's just going to prime the tip. I'll just clean it off because it's been sitting on for quite a few minutes. So my tip is slightly flat, like a chisel, so I need the flat side up. If you're using a round tip, which is pretty common, then you can use any part of it. So I'm just going to maneuver my solder. Once you've got it in the right spot, it's not too hard. You just raise and lower your hand to dip solder onto it. So I'm going to put a tiny bit of solder onto the tip, and then I'm going to hold with the wire tilted upwards, so away from my hand, upwards towards the camera. So that's because the heat's going to rise up the wire, so my fingers aren't going to get too hot. We're then just going to make a good connection with the wire so that the solder actually wicks in to the filaments. You probably won't be able to see this on camera because it is very small. That smoke coming off is actually just the flux coming off coming out of the solder. Like I mentioned before, that's there to make a nice shiny joint. So hopefully we can get close enough for you to see that. Ooh. So yeah, you can see it's nice and shiny now. It's like almost mirror polished. So that's a good tin. It doesn't have any lumps of solder on it. That's a good tin. Let me just check the other side. Yeah, that's good. And that's just for reference, that is the bad side, or the non-tin side. You can see just from sitting on the table, it's got a little loose bit there. So the most important thing with tinning is not to take too long, especially unless, because you're using the resin core solder, flux core solder, whatever you want to call it. The main thing is just going to be to do it relatively quickly. Like, you don't have to panic, but you don't want to sit here trying it for 10 minutes. And like with anything, it does take a little bit of practice to get nice and quick at it. There we go. You won't be able to see this on camera because it is very small, but you can actually see the solder when it gets heat. You can just see it go foof, and just like a spill. Right, so that's one wire. Do the black one now. Oh, this long one's going to be a little more of a challenge. It's also important not to take too much time if you're doing it this way, because you are holding the wire. But that's just something that comes with practice. As I said, helping hands are a really good way to start with doing this sort of thing. Okay, so we've got our two wires. That's ready. Now we've got a connector, a resistor, and an LED to join up. Now we can really do the resistor and LED any way we want to do it. It needs to be in line with the with the LED. The resistor needs to be in series with the LED. So I've got my little clip connector here. I'm actually gonna start with the LED, with the resistor. Sorry. So first of all, I'm going to trim off the leg to match the length of the little stump that's sitting there. And we just want to solder those together. So like I did with the resistor, with the wire, sorry, I'm going to pre-tin the stump of wire that's sitting out. Now, just to make this extra simple for myself, I'm going to pre-position the LED using my helping hands. So like I say, you don't need one of these things, but it is very helpful when you're doing stuff wire to wire. Circuit boards, not so much of an issue as long as you've got something heat-proof that you can put it on. So I've got that in place. I'm going to put a bit of solder on the tip just to have a good connection, and then we're going to... And once again, you can kind of see if you've got a good joint because the parts look physically like melded together. If you turn the thing around and you can distinctly see that there is like a second wire there, then your joint didn't get hot enough. But hopefully you should be able to see we got a nice shiny joint around there. So that's sorted. Now so we need 2 wires now. So I'm going to just trim the excess leg off that resistor because it really doesn't need to be that long. Something to note with this circuit, doing wire to wire like this, is the weak points in it. You've got a couple of weak points. And this sort of comes onto the mounting thing, is we're really just trying to reduce weak points because you probably know like when you bend wires over and over again, like they tend to break. And these wires are very fine, and the ones that go to the components are also solid, which makes them less durable to bending. So you basically want to, the whole goal with mounting LEDs and making these circuits when they're loose like this is just to not have as little sort of bend points as possible and to do everything you can to stop it from bending sharply. And you can see obviously I'm putting a long wire on the end of this resistor here, and that resistor can bend all over the place. So once I solder this on, now the wire's already pre-tinned, so I don't really have to worry too much. It's a lot harder doing this on camera because it's like usually I'd get in really close, but I can't because then you wouldn't be able to see. Okay, so that's joined on. So first of all, before I do anything else, I'm going to grab a small piece of the heat shrink that I mentioned earlier. Which, do I have one small enough is the question? Yes, I do. So heat shrink shrinks to about half its size. And I only need about half of it. So this is going to do 2 things. One, it's going to protect that connection that I just made. Now I would usually suggest testing your connections first, but I can tell that this is pretty good. So all I'm going to do is put that bit of heat shrink across the thing like that. So it completely covers the the resistor, sorry, and it completely covers the joint. So when I go and shrink this in a moment, just bear with me while this heats up. There we go. Actually, I'll try and do this closer to the camera so you can hopefully see. So I've gone a bit high. So yeah, it's going to do 2 things. It's protecting the joint that I've just made. So it's going to protect it from the elements, sweat, sweat in particular. Sweat in particular is more electrically conductive than standard water. So you always want to make sure you're not touching your circuits, especially if you've got a lot of LED strip or something. And the other thing it's going to do is give a little bit of strain relief. Now I probably could have made that longer, or I could put a second layer on because it's only just covering the wire there. But for the purposes of today, I'm just going to save this bit for later. Right, so the next step is we need our other wire. Pretty self-explanatory. Oh geez, I hope I put that on the right side. Oh, good. Always check which side. So I've already made this side. So they've got to go red to red and black to black, or red to positive, black to negative. So we'll just position that in the jaws again. Again, the helping hands make wire to wire very easily, but much easier. Just because like it's very difficult to hold 3 separate things. There we go, another nice shiny joint. And then we'll just pop another bit of heat shrink on there. And shrink it down. Just going to turn my heat gun up a bit because I had it on a very, very low temperature. Again, you don't need one of these fancy little heat guns. This is just really convenient for my use at the moment. Just making sure I get all sides here. I used to just do this with a little cigarette lighter or even just the same heat gun you'd use for, you know, warbler or foam work. Works perfectly fine. Okay, so we've now got one side of our circuit. Now we've already put our resistor in there that we calculated before. So now we just want to add the LED. Same rules apply, just now we can't put heat shrink on from this side. So I'm going to preload the heat shrink onto the wire and then get it as far away from where I'm soldering as possible. That may seem like really dumb and like a no-brainer, but the amount of times I've forgotten the heat shrink, like I have to remind myself every time because it's so easy to just forget about it and then you have to undo the work you just did to put it on and then redo it 2 seconds later. So yeah, we're going to get them as far away as possible so that none of the heat comes up the wire. And then I'm going to just trim down that extra long black one. Sorry, you can't see what I'm doing. Okay, now I said before the little flat side is the negative or the long side is the positive. By the flat side, I mean actually on the casing. And because I don't want these really long legs. Oh, now from here, as I said before, if we were mounting it in a crown, what I could actually do is, where's something very flat so I don't rip that'll do. So I'm just going to use something just to butt up against the LED. This is the thinnest thing I currently have on the table, so I'm using this. But I'm going to bend these legs to a right angle. And the reason that putting this little card in here can be important is sometimes these legs will just snap out of the casing. So this helps it not do that. So we'll just do a nice neat bend like that. And now instead of having a long LED, we've made a stubby one. So I'll trim those up to be about the same length as my wires, or the stripped ends of my wires, I should say. Put that in the jaw. Another thing to note is these particular like plastic bulb LEDs are pretty good. And now I've lost track of which one was which. That's the danger of cutting the legs off. Let me just double check. Yeah, I thought I had the right side. All right, so negative is the closest one to me, the little flat point. So we're just going to sit that in there so it's like... Now I got the heat shrink? Yes, got the heat shrink. Okay. So again, we just go and do the exact same thing as before. There we go. Again, all that smoke is just the flux. My iron's not actually hot enough to vaporize the lead. But if you have like you decide to just use a wood burner or something like that that doesn't have a good temperature control on it, just be aware that you really want to maybe put a fan just below your face so that you don't get any of the smoke. Because it's better to be safe than sorry. And some of those things do go very, very hot. And we'll just repeat the same, clean my tip because it's getting a bit chunky. Oops. And then again, just a little dab so we can make a good connection. And we just feed a couple of millisolder into there. And there we go. All right, now before I heat shrink, because you can't reuse heat shrink, you just have to cut it off. So what I'll do is I'll connect my battery up and just quickly test this circuit. And there we are. So it lights up, quick test. So go through, take the wires out, and we'll run this heat shrink all the way around. So again, the heat shrink's doing two things. It's protecting the circuit a little bit, it's stopping the wires from joining together. But it's also giving a little bit of strain relief so that the wires don't just snap off. It's not giving much, it's not doing much, but it's mainly just protecting from the elements. If you wanted to protect this particular type of thing more, I would generally, once I've verified it's all working, I would put a dab of hot glue in here and just make it's called a strain relief, but like whenever you have like a cable, let me grab the one off the side of the table here. When you have that little extra bit of rubber there that just stops it, helps to stop it from bending sharply. All right, so that's as far on as they're gonna go. Untangle my heat gun here. We'll just go up and shrink these down. How much time we got? Not too much. So there we go. That is a really basic LED circuit. It's got a little connector so you could mount this in something and take it out. Very easy to replace battery. Not the smallest battery, but again, you could redo this with, like a coin cell or 2 coin cells or something. You could get a much smaller battery pack. I just happen to have these handy. And yeah, so we're pretty much done in terms of theory we want to cover. I wanted to cover today. I'll show you there. We got a nice thing. So for something like this, these particular LEDs are cool. If you wanted to have something a little less directional, I carefully didn't bring it, but you can file the tops of these flat because the bulb is quite round and designed to be a bit of a lens. So you can go through and sand these down with a file or with sandpaper, and that will spread it out into a much more diffused dot. We've also got things like plastozote, which is hard to see under the studio lights, but you can see that it does spread it out quite a bit. That's a 6mm sheet. So where are we? Let me grab this pink LED strip again. So I'll clear all the extra stuff up so we don't have a short or something. So let's just say you want to just light an area quite smoothly. So we'll grab our battery pack, connect it up. So you can see it's spread it out a little bit, but it's still dotty. But let's say we wanted to light that whole panel. So there's a couple of different methods. You can extend the distance away from the panel. Now this isn't good conditions because it's like a grey cutting mat, but if you paint the underside reflective, it helps, etc., etc. Like any reflection you can do helps. But you can kind of see once I'm probably 4 centimeters away, it does get quite spread out. But we're losing quite a bit of light there. So say if you wanted to light this entire panel, you could do that, have a few strips. That's one method. The one I prefer, because I find it just has a very aesthetically pleasing light personally. You might disagree and feel free to disagree, but I'm just sort of showing what options we have just with the one LED strip. So as long as you paint the base white or use something reflective, don't use aluminium foil unless you're very careful with it, obviously because it's conductive. But you can kind of see, it's not the best example, it's usually quite a bit better result than that, which you'll just have to take my word for because I don't have anything to mount it into currently. But you can kind of see there, lift it up, it looks more like that. Mounting, again, is a bit of an art form, but there's really depends on how you want stuff to go. So let's say you're lighting an entire suit of armor, every piece is lit. So for a start, mounting all the LEDs, I think, is going to be fairly similar across the whole project. You're going to put the lights where they give you the effect you're looking for. Then all you want to do is secure the LED strip, secure the wires going to the LED strip. And usually, if it's, and then depending on what sort of exactly you have, you might need a connection to outside as well. And usually what I would do is secure absolutely everything. Because yeah, the stress and tension and any hard edges and like folding and bending, not bending, but like creasing the wire is what's going to kill the project or sever the connection to the LEDs. So yeah, it's just all about securing it in place without causing stress and tension. The other thing is as well is how you're going to power them. In a big bulky suit of armor, it might, if there's big gaps between parts of your costume where you don't have any ability to hide wiring, like you might need to maybe consider putting battery packs in each part, which is very easy to do with like alkaline batteries, but obviously you're going to be running through a lot of batteries that way. So on the other extreme of that end of the spectrum, I'm just talking with armor suits at the moment, would be to have one central battery pack and then then have wires coming out. Now you can obviously make a big wiring harness essentially that just runs up through your body or under your bodysuit if you've got one, if you can hide it again. And then you can just have one larger battery pack in a belt pouch or hidden in a backpack or wherever you can creatively hide it in your costume. It's really going to depend on what you've got available. I wanted to talk a little bit about Arduino as well, because I'm sure there's people watching this that have probably seen some projects from Kamui Cosplay or other people on the internet that use the programmable LEDs and have really cool effects. It is a whole nother ballgame, but it also kind of, in some ways, is easier because when you're working with this programmable LED strip like this stuff, you supply the 5 volts to it, but all of the other stuff, how bright you want it, what color you want it, is decided in the code. So you get a lot of flexibility and you can do pretty much anything you'd want to do with it. I would suggest if you're interested, there's a lot of educational stuff around the internet. Adafruit has a really good range of tutorials. YouTube, once you look up, how to use like the NeoPixels, which is the Adafruit brand of LED strip. There's lots of different tutorials on that. The Arduino coding software itself in particular has examples built in once you install the appropriate library to talk to the LED strip, which for those who are interested, it's the one I use is called Fast LED. But yeah, that's pretty much all I wanted to cover today. Thank you for watching if you've gotten this far. You can tell I really enjoy electronics. So again, I'm from Lumin's workshop. So if you have questions about your project and you're wanting to light something, but you're not really sure what to pick, you can feel free to contact us via email, or we also have a Discord now, which is linked at the bottom of our website. So you can come in there and we've got a ask for help section. So you can talk directly to myself, or there's many other people in there who are really experienced with LEDs as well. If you're looking for LED supplies, again, we do have some of the supplies at Lumin's workshop, mainly just LED strip and battery packs. But you can get, if you're wanting programmable stuff, if you're wanting something more unique. So yeah, again, thanks for watching. I hope you've learnt something and I hope you've had fun. And good luck with it all.